Hi, my name's Keith McManus. I work at GE Research in Niskayuna, New York, and I manage the combustion organization at our research center. I'd like to spend some time this morning to give an overview of gas turbine combustion. Specifically, I'd like to talk about current and future trends. So I'll be walking through an agenda shown here. Start out quite simple. I'll give an introduction to gas turbine combustion, showing examples of both ground-based configurations as well as aero engine configurations. The second section will go into more detail about aero engine combustors and combustor design. I'll go through requirements, what our development process typically would entail, and then I'll talk a little bit about low emissions designs and typical configurations or strategies that have been taken in order to produce low emissions combustion systems. Then I'd like to talk a little bit about two areas of fundamental research that have been critical in our area. The first are fuel sprays, just fundamental fuel spray physics. And then another area that has been quite active over the past couple decades, in fact, is the area of combustion dynamics. In the end, I just want to point out a few future trends that we're starting to see and show future technology areas that are active, and we can expect more activity in the future. On this slide, I'm showing two products that GE produces. On the left-hand side, it's a power generation gas turbine. This is what we would call a heavy frame gas turbine. Typical power outputs from this type of a machine would be 200 to 300 megawatts. On the right-hand side is a jet engine, which is this particular version is a high bypass ratio turbofan engine, and we're one of the largest suppliers of these engines for commercial aircraft. Now, the combustion chambers, the combustion systems for these two devices are quite different. And I'll show an example for the Powergen gas turbine first. In GE's heavy-duty gas turbines, we tend to use what we call a can-annular system. So the combustion chambers are actually oriented around the periphery of the machine and as individual cans that then feed into an annulus that enters the turbine. So there's a couple of features in a can-annular approach versus, say, an annular approach that make it attractive. One is that we can actually test a single combustion chamber in our laboratory. The other thing that makes this type of configuration attractive is that it's easy to replace in the field. The combustion system itself is devised of a number of different components. Up toward the front end of the combustion chamber would be fuel nozzles, and these are devices used for efficient fuel-air mixing and also to add swirl to the airflow. The fuel nozzles would be placed inside what we call a cap, which is the front or head end of the combustion chamber. And then a combustion liner would be attached to that cap. And at the downstream end of the combustion liner is a transition piece that transitions the flow cross-sectional area from a round shape to a annular slice. Now, on the contrary, aviation gas turbines tend to have annular configurations for their combustion chambers. And so I'm showing a cross-section of a typical combustor used in a GE turbofan engine. So like I said, they're annular combustion chamber shapes with multiple fuel nozzles and air inlet swirling features at the front end of that annular chamber. So this is predominantly the configuration used by all aviation turbine manufacturers, so it's sort of the standard of the industry in terms of configuration. I'd like to spend a few moments to talk about aero engine combustor design, to try to give you an appreciation for all the elements that go into the combustor design, development, and then ultimately the certification process. So let's start by looking at the mission requirements and the range of conditions that the combustion system has to operate over with good reliability and performance. On the left-hand side of the slide, I'm showing a couple different turbine engine applications. The upper panel shows a high bypass ratio turbofan, which would be typically used in a passenger aircraft or freighter. On the lower panel is a lower bypass ratio turbine engine, and that style is more found in military applications. On the right-hand side of the slide, I made a depiction of the pressure and temperature ranges over which a gas turbine combustor needs to operate, and I superimposed on that operating line examples of where different portions of the flight cycle would be represented. So as we light the engine off on the tarmac and idle, the pressure and temperature are relatively low, in the order of a few atmospheres and a few hundred degrees Fahrenheit. As we accelerate the engine for takeoff or to go to max power, we can reach pressures and temperatures on the order of 60 atmospheres and nearly 1,500 degrees Fahrenheit. Then we'll back off on the throttle during cruise. Descent, we back off even more, and then landing is a low power condition. Now, I will point out that there is a very low pressure condition where the combustor has to be capable of relighting, and that is when we have, for example, at altitude, a flame out of an engine, and then have to relight that engine under very severe low pressure and low temperature conditions. But that is an important requirement for these engines, and it's an FAA certification point. Now, the performance of the combustor is measured in many ways. The requirements for the combustor performance and operability are imposed by a variety of forces, including regulatory agencies, airline, the end users, the airplane manufacturer, the type of engine that it's going into, of course, and also the performance can be influenced by natural conditions where the engine may be operating, or environmental conditions. So as you can see, this is a pretty busy cycle or play of different parameters. All of these performance aspects are important. They all can contribute to the operability and reliability of the system. And we can only reach a balanced design after detailed analysis and testing of a combustion system. So I'll be going into more detail in some of these performance measures. Most specifically, I'll talk about emissions requirements and dynamics issues. This shows a progression that our company would normally go through to develop a new combustion system. So on the top, we're listing technical readiness levels or technology readiness levels. And then below each of those TRL levels, if you will, we show an example of what the design and test activity would tend to entail. So we would start with the concept, and then we'd start working on both analytical and experimental aspects of evaluating those concepts. This would progress to what we call single nozzle testing, or single nozzle flame tube testing, which is where rather than testing an entire annular combustion system with multiple nozzles, which would be, of course, the final product, we start with just single components. Then we would progress to a multi-component or multi-cup test shown under TRL4. Finally, we would go to full annular and then engine demonstration testing. These are after all the issues that arose during the earlier development testing were ironed out, and we're narrowing in on a design that looks like it will meet all the requirements. And ultimately, to certify that engine for service, we would put it on our flying test bed, which you can see a picture of it here. It's a 747 aircraft where we can replace one of the engines with our certification engine and then fly it on that aircraft and evaluate its performance under normal and typical flight missions. I want to point out that basic combustion research, really is coincident with the TRL 1 through 3 phase of this development process. In this slide, I'm describing the typical anatomy of a jet engine combustor. So this is a particular style of combustion system, and I'll talk more about other options later in the presentation. But the purpose of this slide really is to give you an appreciation of the different flow physics that occur in this engine or in this combustion system, and where we have to pay attention to different physical processes. So I'll walk through quickly. The compressor discharge air is coming into this combustion chamber from the left-hand side. We have turbulent flow with large-scale structures being shed. The air then enters some of the air enters through a swirler that is surrounding a fuel injector. So you can see a fuel spray, which is at the core of a swirling flow. There's a vortex breakdown downstream of that swirling flow that serves to stabilize the flame. And so there's a vigorous turbulent mixing process between the fuel and air going on in that region. The flame stabilized in that recirculation zone. And then downstream in this type of combustion system, we have dilution air entering through the combustor liner, and those are depicted by those black arrows. So we have essentially jets in crossflow diluting the combustion gases and also progressing the combustion process. Then we have downstream where the hot gas enters the turbine, subsonic flow. By this time, we expect all the combustion reaction to have taken place. The other thing that we point out in this chart is that there is a boundary layer along the inside surface of the liner that's composed of cooling air, but also has, there can also be combustion reaction associated with those boundary layers. So it gives you sort of an appreciation for the complexity of the flow field in this type of a combustion system. Now, what I just described was what we call a rich burn combustion strategy. And what we mean by rich burn is that in the front end of that combustion chamber, where the swirling air and the fuel spray enter and mix, the overall equivalence ratio in that region is fuel rich. So in the depiction on the right hand side, where we have temperature versus fuel air ratio, we actually, in the head end or in the front end of this combustion chamber, we start in a fuel rich condition. So that gives us a somewhat lower temperature than the stoichiometric value, which would be at the max or near the peak of this curve. So we start fuel rich, and then with this air dilution that comes through the liner and rapidly mixes and burns out the excess fuel and also dilutes the mixture to end at a lower temperature, lower overall mixed and burned temperature. The strategy is to transition quickly from that fuel rich condition to a fuel lean condition to avoid those very hot regions of stoichiometric combustion products, which would lead to high NOx levels being generated, high thermal NOx levels being generated by those high temperature regions. Now the alternative is what we call lean burn combustion, which is exactly what you would expect it is. And that's where we, rather than having these dilution jets come in to dilute and further react a rich primary zone, we actually bring most of the air through the front end of the combustion chamber, mix it with fuel prior to the flame front, and then burn in a fuel lean mode, both in the front region of the combustion chamber and maintain that lean burn condition all the way through. Now, of course, there would be some air coming through to cool the liner, which does reduce the overall equivalence ratio, and that on the right-hand plot is depicted as a shift from the upper bubble to the green bubble. So we avoid high NOx production by starting lean and staying lean. So just a few notes on rich burn versus lean burn combustion. Rich burn has been the strategy that has been used for many decades. It's the strategy used by most engine companies in their current products. There's reasons why we stick with that to some extent. It's less complex, which leads to a lower cost strategy. The technology is mature. The combustion is very stable by virtue of that rich primary zone. There, however, can be durability issues, and also it is not capable of the extremely low emissions levels that we're able to achieve through premixed lean burn combustion. So on the contrary, the lower figure shows a lean burn combustor. You can see the flame is not sooty like the rich burn combustor. So it has great benefits in emissions, both for smoke as well as NOx emissions. Now, this does come at a price, because as we have found also in our Powergen gas turbines, where we are implementing lean premixed combustion strategies, we find that stability is compromised, both from a flame fundamental static flame stability perspective, as well as a dynamic or thermoacoustic instability perspective. And I'll go into more detail on that phenomenon. This is a chart showing sort of the technology evolution at GE. So I talked about, I think, the furthest to the left and the furthest to the right, but we've actually looked at other strategies aside from just the lean burn and the rich burn. We've looked at fuel staging concepts, and that's shown in the center panel, where we have a double annular combustor. Now, in this strategy, the fuel injection is achieved by using two separate fuel circuits. And you can imagine, for a low power operation, we can just light off the flame associated with one of those injection points. And then for higher power operation, we can stage on the other circuit. So that's a strategy to do to be able to burn lean and stage the fuel in a annular combustion configuration, dual annular combustor configuration. So our most recent products, the GE-NX and the LEAP, and actually the GE-9X, which is just recently certified, those all use this twin annular premixing swirler premixing concept, or we call it TAPS. It allows for lean burning. We get a 50% NOx reduction, and allows us to achieve combustion within a shorter distance. And we actually stage fuel within the swirler, rather than in the dual annular combustor example in the center, where we stage the fuel spatially in two different regions of the combustion chamber. We stage the fuel within the fuel nozzle itself. I'd like to say a few words about combustion emissions. emissions are regulated, and the regulations are arrived on by an organization called CAPE. It's a international organization composed of governments, industry, affiliates, airlines, and others, and they collectively come up with emissions requirements for aircraft engines. So a few notes: NOx is formed at high temperatures in the combustor, primarily at high power conditions. Unburned hydrocarbons and carbon monoxide result from incomplete combustion of the hydrocarbon fuel, and these emissions are produced primarily at low power conditions. CO2 and H2O, of course, are stable products that are not harmful or regulated, and sulfur dioxide is formed by combustion of sulfur that's in the fuel. On the right-hand side, it gives you an idea of what the emissions goals are that have been laid out by CAPE. And I think the point that I want to make here is that the regulated emissions, NOx, CO, and unburned hydrocarbons, are trace species. Now, what we see coming in the future are more stringent regulations. There has been talk by the CAPE committee that sets these emissions regulations of changes that will be likely coming in the future. Right now, the way that NOx is measured, it's really only ground level NOx that is regulated, not cruise. However, most of the NOx created by turbine engines or aero gas turbine engines is produced at altitude. So there was talk, because the cruise NOx does affect climate and global air quality, there was talk that cruise NOx will start to be regulated. And in addition, there's also a likelihood that non-volatile particulate matter will also be regulated in future goals. I'd like to talk about two research areas that are fundamental research areas that we've been involved with, and I think are quite active in the general field. First is liquid spray physics. I'll show some examples of some measurements that we've done in our lab and in other labs regarding the details of liquid sprays. The other area that I wanted to highlight is thermoacoustic instability, or in the industry vernacular, this is known as combustion dynamics. So liquid fuel spray physics are very complex. It's one of the more complex aspects of the physical processes that occur inside the combustion chamber. So we've just pointed out a few processes. It starts with the fuel injection, the jet or liquid fuel penetration in an airstream, fuel atomization, droplet formation, then subsequent fuel evaporation, a phase change. This can be very complex, especially when we're in a supercritical flow regime. The fuel air mixing is a very important process, especially in these low emissions concepts where we're trying to rapidly mix fuel and air even prior to the combustion front. And then ultimately there are chemical reactions that result in heat release from the combustion process. So along with all the testing that we do, we also are trying to mature CFD methods to help our design process. In particular, in our CFD models, the liquid fuel injection models are woefully inadequate to represent this large range of conditions that we experience in the combustor. So it would behoove our community, our industry, to have better fidelity in these models. We need improved models if we're to use these tools for combustor design, and we need good validation data to help develop these models. So that's sort of the motivation behind some of the examples I'm going to show. So even fundamental studies of liquid jets in crossflow or fuel injection jets in crossflow are valuable. In our high pressure ratio gas turbine engines, we're actually injecting the fuel at supercritical conditions and under certain flight regimes. And so the way the fuel mixes, changes phase, and ultimately burns is of great importance. In these two images, I'm just showing an example of some measurements that we did in our laboratory using nitrogen as a sort of a fuel surrogate in a non-reacting experiment. On the left-hand side, we have subcritical injection of a liquid nitrogen jet into a nitrogen or gaseous nitrogen free stream crossflow. On the right-hand side, we're injecting that liquid nitrogen jet into a supercritical crossflow. So you see very different behavior. There's nowhere near the apparent penetration of the jet when it's at a supercritical condition. So the trajectory and the mixing in these two extreme cases are very different, and it's important for us to understand how to represent this behavior in our models. This is an example of a measurement that we've done in collaboration with Argonne National Lab, where we're simply wanting to image the fuel spray characteristics at the exit of a liquid fuel atomizer. And that atomizer is shown in the upper left photograph, and we're zooming in with the red box on the region of the spray that is in the field of view of this X-ray movie image that we're watching. So this is, to our knowledge, the first time a real fuel injector was X-ray imaged at the Argonne lab. It shows very interesting and complicated features in the fuel spray region. So there is a liquid sheet that forms at the exit of that injector and then breaks into ligaments and finally droplets. So the physics of this process are important to understand for different designs. This kind of a measurement can offer liquid sheet thickness data and break up dynamics, and ultimately it would be useful to have droplet statistics also for validation data for our models. This is an example of of a measurement we made in one of our test single nozzle combustion rigs, where we oriented a laser sheet downstream of these two fuel injection systems. So we're looking at the front end of a combustion chamber. We have on the left-hand side a rich burn configuration. On the right-hand side, it's a lean burn configuration. And by looking at these movies, there's a stark contrast in the unsteadiness and in the intensity of the me scattering off the droplets, and there's also a unsteadiness in the circumferential distribution of the me scattering signal. So this kind of a measurement is useful in evaluating liquid spray characteristics, and I should say this is in the presence of combustion. So downstream from this, these injectors are combustion processes. This is an example of a measurement that's also of great value, and this is a measurement of fuel air mixing downstream of a lean burn fuel injector. So in this case, we've used acetone as a fuel surrogate in a non-reacting experiment. So the acetone acts as a surrogate. We were able to match essentially the evaporation rate for certain conditions of interest, and it also allows us to match fairly closely the momentum, jet to cross flow momentum ratio. And so there's a similarity between this substance and Jet A. So we've successfully used that to look at fuel air mixing in real injector flows. Here I'd like to discuss combustion dynamics, or these thermoacoustic instabilities that I mentioned earlier. Now, combustion dynamics is a problem that has become quite extreme in our modern low emissions combustion designs. So what this instability is driven by are interactions and feedback loops between the combustion process and acoustics of the system. So we've shown in this diagram on the upper left that and this is just an example, there can be many more complex components and interactions that lead to these oscillations in flame heat release as well as pressure oscillations. But this is fairly typical that acoustic resonances in the system can drive or can be excited and in turn cause fluctuations in the fuel and air flow rates, for example, which then manifest in flame heat release oscillations. And the end result can be quite dramatic and detrimental. An example of one aspect of how detrimental it can be is shown in these lower right-hand figures, where this is for a power generation combustion chamber, but it shows that actually the combustion dynamics broke part of the combustion chamber due to the high amplitude pressure oscillation levels. In these oscillations, or these dynamics, can occur over a broad range of frequencies, everything from tens of hertz to many kilohertz. And so, and how they occur and at what frequency they occur depends on a number of different aspects, but it suffices to say that this phenomena continues to be a very, very difficult problem to solve, and there's been intense research in this area to study various physical processes that contribute to this thermoacoustic phenomenon. An example of some of the work we've done is shown in this slide. We have an experimental facility where we can put a fuel injector for an aviation type combustion system into a chamber, and then we have full optical access to apply both laser-based measurements as well as other more traditional probe-based measurements if we'd like. So this facility has capability to go to very high pressure and temperature, representative of high power combustion conditions in an aviation gas turbine, and we've leveraged this facility to do some interesting work in the area of combustion dynamics. This chart shows a number of different measurements that we made in that chamber. So I'm going to just build this chart. We're looking first at on the top. We used a 3D PIV system to make velocity measurements. On the left-hand side, that was the quiet case. On the right-hand side, it's the loud case. You can see some fundamental differences in the velocity components associated with these two conditions. In the lower panels, you'll see on the left-hand side the mean intensity of the fuel spray. So you can think of that as a fuel distribution. And these are axial cuts, or cuts in axial planes downstream from the fuel injection. On the right-hand side, those are actually phase-locked images of the fuel spray and combustion distribution. And in the loud case, you can see these large oscillations in the flame structure that's associated with a high amplitude pressure oscillation in the system. Just like to take a few moments to talk about some future trends. I'll give an example of an advanced architecture, example of an advanced cycle, and also to just say a few words about decarbonization. So advanced architectures can be embodied in many different ways, but I wanted to show this example of a program we've been working with the Department of Energy to look at the possibility of combining the functions of two components, two otherwise separate components in a gas turbine. And those components are the combustion system and the stage 1 nozzle, so the stationary nozzle at the first stage turbine. So we've been working this program leveraging advanced concepts, including additive manufacturing, to try to realize the combined system system of marrying these two components into a integrated system. Now, there are benefits that come with this, not the least of which is we can minimize the amount of cooling that we need for both these components by tying them together in this way. Also, we believe that this type of a strategy could lead to a lower cost. Another area of interest and of great research activity over the last 5 to 10 years has been incorporating a detonation combustion in turbine engines. So here's an example of where we could envision using a rotating detonation combustion system in a Powergen gas turbine. So the upper left-hand graphic shows a Powergen turbine cross-section with the combustor can pointing or canting outwards. There's a purple region, which is where the rotating detonation combustor would be located. So we've done cycle studies, looked at how we could anticipate improvements in the gas turbine performance by implementing this kind of a pressure gain combustion strategy. And you can imagine that if we're using detonative combustion to not only release heat, but also increase pressure in the system, we may be able to remove compressor stages, and that would give us an efficiency advantage. So our system efficiency calculations show that by moving to a rotating detonation type system or strategy could give us a simple cycle thermal efficiency increase by up to 14%. And in the combined cycle application, combined cycle case, where we do have a bottoming cycle on the connected to the gas turbine, the efficiency gain would be less, but still it would be, say, 1 to 3%, which in the world of power generation gas turbines, that's actually a huge gain in efficiency. Now, the last thing I wanted to touch on is the trend of decarbonization and how we're beginning to think about addressing that in the aviation and power gen gas turbine world. So initially, I think the CO2 emissions reduction that the IATA is targeting, initially we will address them as an industry through advancement in technology, essentially doing what we already do, but doing it better to improve the efficiency of our engines, and therefore require less fuel burn per mile of travel. Advanced cycles also could play into efficiency improvements and net gains in propulsive efficiency or system efficiency. Carbon neutral fuels, also a big component of the overall strategy. We are certainly working on addressing our capability of burning biofuels in our engines. The final sort of what I labeled as a paradigm shift would be to actually go completely to a non-carbon fuel, like hydrogen. And so there's been a lot of interest in our industry in looking at hydrogen as a fuel, not only for power gen land-based gas turbines, but also the possibility of using hydrogen for aviation turbines. So this is certainly not a new concept, but it is a concept that's being revived in a way that is very exciting. And so I think we can expect to see a lot more activity in this space. And I think with that, I'd like to stop now and take some questions. Thank you very much.